After the failure strength tests, we discussed the fracture mechanics tests in module 15. So we have seen the failure strength tests. Let's now see the fracture tests, mode 1, mode 2 and mixed mode. The most common fracture energy test is the DCB test, that means the double cantilever beam test. You have here the two specimens commonly used. So we have two substrates, the adhesive, there is a pre-crack, and we load the specimen during the test. We record the load, we record the crack length and this displacement, and we can deduce the fracture energy. Let me show you these specimens. So in this case we are talking about aluminium, and there is an adhesive film between the two, and the two holes here that allow to load the specimen in mode 1. All right. So that's when we have thick substrates. If we have thin substrates, then we can bond tabs at the edge that will allow to load also the specimen in mode 1. That's for metallic substrates. For composite substrates in general, we use thinner substrates. Again, two composite plates. There is the adhesive here in the middle. All right. In this case, well, you need to bond a tab, or you can bond a plastic, a piano hinge, sorry, like this case here. You see, we bonded piano hinge, and then we can load the specimen easily in mode 1. Okay. How do we deduce the fracture energy? Well, you can start with the total potential energy, which by definition is the difference between the elastic stored energy and the external energy from the load applied. So it comes to this, the difference between the two. The displacement, this displacement can be written as a function of the compliance and the load. The compliance is the opposite of the stiffness, and the displacement is obtained or can be obtained by the beam theory. So we have an explanation then for the compliance. The total energy then simplifies to this. We have the compliance, or as a function of the crack length, you have here this expression. By definition, the strain energy is the variation of the potential energy per unit area, or you can do it like the variation of the compliance per crack length. The final expression is this. You have the load here, the crack length here. So really, during the test, you need to measure this and the crack lengths. And from this, you can deduce the fracture energy when the load corresponds to the moment where you have propagation of the crack. The only difficult thing here is to measure the crack lengths. This will depend a lot on the operator. So many times we prefer to use another data reduction technique which does not need the crack length measurement. It's called the compliance-based beam method, and in this method the crack length is deduced from the compliance. From this and from the load you can deduce the compliance, and it takes into account the fracture process zone, which is damage ahead of the crack tip that you cannot detect if you use a crack length optical measurement. This is especially relevant in mode 2, because in mode 2 the two arms are against each other, and it's even more difficult to detect the crack tip. In mode 1 it's easier, but in mode 2 really a nightmare. So the CBBM makes really sense when you test in mode 2. And talking about mode 2, you have here the most common ones. Bear in mind that for mode 1 we have a standard, but for mode 2 it's still controversial, and depending on the lab you have various techniques used. You have the end notch flexure, or the end loaded split, or the 4-point end notch flexure. There are various techniques used. But in fact, in reality, joints are loaded in mixed mode, a mixture of mode 1 and mode 2. And again, you have some techniques, some specimens in the literature. Various, you have the single leg bending, the asymmetric double cantilever beam, but there is not a universal specimen for this type of loading conditions. That's why at Porto we decided to develop this mixed mode apparatus. You have here an image of the apparatus, and you use always the same type of specimen. We are talking about the DCV according to the international standard. And with this device, by changing here the loading location, you can test from mode 1 up to pure mode 2. And you have in between dozens of combination of mixed mode conditions. And you always use the same specimen. This is the mixed mode condition of 45 degrees. That means half mode 1 and half mode 2. This is the 0 degree condition, corresponding to mode 1. This is the 90 degrees condition, corresponding to mode 2. It's very easy to determine the fracture envelope in a graph G1 versus G2, strain energy in mode 1 versus strain energy in mode 2, and you have the results obtained with that device here, 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 and you see you have many mixed mode conditions. Of course, we have validated this with standard specimens, which are in blue, and you can see that they compare very, very well. To end, you have here a table which gives properties, fracture properties, but not only, the tensile properties, shear properties for many adhesives that we have tested in the lab, for epoxies, polyurethane, modified acrylics, silicones. You have a lot of very, very useful properties for joint design.